All right, welcome everyone. We are going to talk a little bit about independence of random variables in this video. So I'm still in our section 4 note packet. I'm on page 7 now. And we will do a couple of small examples of independence, but we'll start with just the definition. And so we're given right away that continuous random variables x and y are independent if and only if um, one or either their kind of equivalent of these two statements is true. So we'll start with the top one first. So if the conditional density of x given y is just the marginal density of x for all values of y, one way you could think about this statement is that it doesn't matter what y is. No matter what y is, you have the same exact marginal density for x. Another way that you could think about this is you could note that, right, we talked about independence way back in section 1, and really this definition isn't crazy different from when we had the definition of independence for events. And so it still kind of has this flavor where the condition part doesn't matter. So when we did events, it was the probability of A given B. Oh, it doesn't matter if B occurred, that's still the probability of A. Similar concept to these densities. So it doesn't matter what Y is observed as, no matter what, the conditional density is the same as the marginal density for X, and vice versa for Y given X. We'll often, when determining if two variables are independent, we will make use of this theorem. And again, I'll kind of note that this is not crazy different from when we used this definition of, or this kind of check for whether two events A and B were independent, to see if you could multiply them together. Same idea. So if the joint kind of factors into the marginal of x times the marginal of y, then x and y are independent. A final theorem that we will make use of is that if x and y are independent, then the support set has to be a rectangle. Note that this is not an if and only if statement, like the definitions were up here. It's just an if statement. So if x and y are independent, then the support set will be a rectangle. But if the support set is a rectangle, that does not necessarily mean that x and y are independent. We can use this, though, mainly for its contrapositive, which says that if the support set is not a rectangle, then x and y are not independent. So that's the contrapositive of the statement. So if we check the support set and it's not a rectangle, we're done. Then that means x and y can't be independent. Done. Okay, so a couple of examples. The first is an example that we worked with earlier in an earlier video, where we have this joint density function. Right away, I'm going to notice that the support set here, we sketched that out earlier. That was a triangle. It is not a rectangle. So a rectangular support would be like x is between 0 and 1 and y is between 0 and 2. So that would be like a rectangular support. This is not a rectangular support. So right away, based on that theorem, are x and y independent? No. The support set is not a rectangle. So x and y cannot be independent. if you're not quite satisfied with the theorem itself, this does make sense intuitively. Um, and it makes sense in the way, so the allowed values for y. So what y is allowed to be, it depends on the value of x that is observed. So the support of y after you observe a value of x, it depends on what that x is, and so there's no way that x and y can be independent. One more example. Again, we encountered this particular joint density earlier in the note packet. So f of xy is 4xy. This time, we've got a support set that is a rectangle. But remember, that's not sufficient. So we can't just say, oh, the support set's a rectangle, so x and y are independent. That's not how the theorem was worded. It was not an if and only if theorem. So we need to do some work. And I'm going to make use of that theorem that says x and y are independent if and only if the joint is equal to the marginal of x times the marginal of y. And so I'm going to calculate the marginal of x first. That means that I want to integrate out y. So I want to integrate from 0 to 1 for xy dy. That, if you do that integral, I'm not going to show all the work, but that is 2x. And so that implies that our marginal density is 2x for that support and 0 otherwise. I'll do the same thing for y. So now I want to integrate out x so that I could get the marginal of y, and that is just equal to 2y. And so our full marginal is 2y, where y is between 0 and 1, and 0 otherwise. And now what the theorem says is to check, what if I multiply those two marginals together? Is that the same as the joint distribution? If it is, x and y are independent. If it's not, then x and y are not independent. So 2x times 2y is 4xy. I'm going to be a little lazy and not do the support and say that it's 0 otherwise, but you'll note that that is the same as our joint density that we started with up here. So, which is our joint. Therefore, x and y are independent. And so one last quick note, I definitely think it's easier to use this this theorem here. So if the support's rectangular, then I think it's easier to use this theorem as opposed to the definition to actually check if two variables are independent. But for me, thinking about it conceptually, the definition is the easier way to think about independence. I like thinking about, okay, so given a value of y, I don't care what that value of y was, x has the same marginal density no matter what a given value of y has been observed as, and vice versa. So given a value of x has been observed, if x and y are independent, then the density of y, it doesn't matter what, if x was 0.5, if x was 0.23, doesn't matter. The density of y is its marginal.